Velan is a global manufacturer of industrial valves with over 1,200 employees and 12 manufacturing plants located in 9 countries around the world. The Velan Universal Steam Trap was introduced for the first time in Canada and the United States in January of 1950. In those days, the predominant steam trap technologies in use were cumbersome, inefficient, and required frequent maintenance. Founder and CEO Mr. A.K. Velan set out to design a steam trap that was suitable for the high pressure and high temperature operating conditions that naval vessels and thermal power plants were being designed around at the time. The operation of this new steam trap was based upon the principle of a free-floating and rotating ball valve placed on the downstream side of a stellite valve seat and being actuated by a multi-segment bimetallic element. The result was a steam trap that combines effective condensate drainage with high energy efficiency and long service life. Energy efficiency and reliability. These are the only two metrics that truly differentiate steam trap manufacturers. Our goal is to help you generate less steam and perform fewer changeouts. That's the Velan promise, quality that lasts. To understand what sets Velan apart, it's essential to look at the other steam trap designs currently dominating the marketplace. The predominant steam trap technologies today are similar to those in use when Mr. Velan set out to change the world of steam traps in 1950. The inverted bucket trap is another technology widely used today. First patented in 1911, the inverted bucket trap operates on the difference in density between steam and condensate. This trap uses a bucket, open on the bottom, to operate a lever valve and orifice located in the top of the trap. In the absence of steam, the bucket sinks to the bottom, keeping the valve in the open position and allowing for free discharge of condensate. When steam or air enters the trap, the bucket becomes buoyant and floats to the top, closing the valve. When the steam condenses, the bucket sinks to the bottom, opening the lever valve and discharging the condensate once again. During normal operation, the steam inside of the bucket is continuously lost through the air vent in the top of the bucket and discharged through the lever valve. In 2017, while visiting a major U.S. refinery, a Velan representative was met with a challenge from a lead engineer. He didn't believe the steam escaping through the air vent actually constituted a measurable loss. This engineer had attended the Armstrong Steam School in Three Rivers, Michigan, where he was taught that inverted bucket steam traps suffered no measurable live steam loss. The Velan representative proposed a controlled laboratory test to settle the debate. The experiment would precisely measure the discharge from a saturated steam line, comparing the performance of an inverted bucket trap against the Velan multi-segment bimetallic design. Testing commenced in August 2017. After 20 rigorous trials, alternating between the inverted bucket and the Velan multi-segment bimetallic trap, the data was undeniable. The results spoke for themselves. We then wrote this white paper, Steam Loss and Inverted Bucket Steam Traps. There is a fascinating footnote to this story. In 1986, Armstrong International ran an ad campaign proving that inverted bucket traps waste less steam than thermodynamic traps. The irony? The very school that teaches that inverted bucket traps lose no live steam actually published data on those exact losses nearly 40 years earlier. Testing shows the steam loss through the air vent to be approximately 3 pounds of steam per hour. This steam loss occurs throughout the entire life of the trap. At current energy costs, the amount of steam lost due to the operation of the air vent is over $250 per trap annually. In a plant with a population of 1,000 inverted bucket traps, the amount of energy lost due to the operation of the air vent is over $250,000 annually. The most common cause of failure for an inverted bucket trap is loss of water prime. As this demonstration shows, if the water prime is lost from the inside of the trap body, the high velocity flow through the trap prevents it from repriming itself. Loss of prime can be caused by exposure to superheat, improper sizing, mechanical wear, or simply too rapid a startup. The Velan multi-segment bimetallic steam trap offers an efficient alternative to conventional steam trap designs. Operating on a thermostatic principle, the Velan steam trap requires no more energy to function than is present in the condensate that collects at the drain point. The Velan steam trap uses a multi-segment cantilevered bimetal stack to actuate the ball valve. At ambient temperatures, the bimetal element is relaxed and the valve is open wide, allowing for rapid discharge of cold condensate and non-condensable gases at startup. As the temperature of the condensate increases to within 3 degrees Fahrenheit of saturated temperature, the bimetal element pulls the valve closed. In the presence of live steam and saturated condensate, the valve remains closed tightly. When the condensate in front of the trap cools to 4 degrees Fahrenheit below saturated temperature, the line pressure overcomes the closing force of the bimetals, and condensate discharge resumes. The Velan multi-segment bimetallic design cycles every 2 to 3 minutes versus every 10 to 20 seconds like other conventional steam trap designs. In the event of a sudden drop of upstream pressure, the valve and seat arrangement act as a check valve, preventing reverse flow in the system. The Velan multi-segment bimetallic steam trap provides rapid, efficient startup of steam distribution drip leg and tracing systems. Due to the advanced design of the bimetallic element, the Velan steam trap collects no more than 12 inches of condensate ahead of the trap at any time, ensuring efficient drainage and preventing the loss of live steam. To better understand this internal operation of the Velan multi-segment bimetallic steam trap, we have constructed a test apparatus to demonstrate the internal workings of the trap. The test rig consists of a steam supply with a constant low-volume condensate flow to the trap of approximately 10 pounds per hour at 100 psig. The piping arrangement includes isolation valves, blowdown valves, and a liquid level gauge for visual detection of condensate. A number of instruments are installed in the pipeline which provide data to a digital video recorder. This digital recorder monitors pressure and temperature variables at various distances from the steam trap. The chart recording demonstrates the efficient operation of the Velan multi-segment bimetallic steam trap. Notice the temperature inside of the trap body at pen 5. This remains below steam temperature throughout the entire opening and closing cycle, preventing the passage of steam across the orifice. However, the temperature of pen 1 at the inlet of the trap rises to saturation temperature at the end of every discharge cycle, ensuring the efficient discharge of condensate from the line. Velan multi-segment bimetallic steam traps offer several advantages over the use of conventional steam trap designs. Chief among these are increased energy efficiency, extended service life, and a high resistance to plugging. When compared to the normal and necessary steam operating losses of conventional steam trap designs, the use of Velan multi-segment bimetallic steam traps presents significant opportunities for cost reduction. Replacing inverted bucket traps with the Velan multi-segment bimetallic design will result in annual cost savings on average of $250 per trap. In a plant with a population of 1,000 inverted bucket steam traps, this is a savings of $250,000 annually. The longevity of the Velan multi-segment bimetallic steam trap has been widely known to major steam users for the past 75 years. Since 1950, Velan has been a pioneer in the use of cobalt-based alloys in critical components of valves and steam traps. Stellite 6 is welded into the seat facings of all steam traps manufactured by Velan. The resistance of Stellite 6 to erosion and wire drawing is over 3 times that of induction-hardened stainless steel. The result is a steam trap that routinely lasts up to 3 times longer than conventional designs under the same service conditions. Velan is currently the only manufacturer globally to use stellite as a standard material in the construction of a steam trap, and the value is well proven. Another design feature contributing to the longevity of the Velan multi-segment bimetallic steam trap is a reduced cycling pattern. The Velan multi-segment bimetallic steam trap cycles every 2 to 3 minutes. At 3 degrees Fahrenheit below saturated temperature, the steam trap is closed tightly. At 4 degrees Fahrenheit below saturated temperature, the ball valve gradually opens until the line pressure fully engages the ball valve and causes the trap to open, similar to a safety relief valve. This opening clears any condensate in front of the trap until the temperature of the condensate gets within 3 degrees Fahrenheit of saturated temperature, and then the trap closes. The result is fewer mechanical cycles of condensate and flash steam, which produces less mechanical wear than rival designs operating with violent blast-on, blast-off discharge patterns. The thermostatic operation of the Velan multi-segment bimetallic steam trap brings a number of advantages to plant personnel. Chief among these is a complete resistance to plugging and freezing. The location of the ball valve on the downstream side of the orifice has 2 major advantages. First of all, when condensate temperatures at the trap drop below saturated steam temperature, the bimetals relax and the valve is forced open by the line pressure. This ensures that the failure mode of the Velan steam trap is always in the open position, preventing freezing, waterlogging, and damage to piping and process equipment. Secondly, the downstream valve design prevents clogging of the orifice due to copper oxides or iron oxides present in the condensate. Most conventional steam trap designs locate the valve on the inlet side of the orifice. This is true for inverted bucket, thermostatic capsule, thermodynamic, and float-style steam traps. When copper oxides are present in the condensate, they build a deposit at the point in the system where the condensate flashes to steam due to pressure drop. In the case of conventional upstream valve designs, this flashing occurs inside of the trap orifice, eventually restricting and blocking condensate flow and resulting in the freezing or plugging of the equipment being drained. The Velan multi-segment bimetallic steam trap with a downstream valve design produces condensate flashing after it has passed through the orifice, leaving any hard mineral deposits on the outside of the ball valve and not inside of the orifice. Our field experience over 7 decades demonstrates that facilities that experience a high incidence of steam trap plugging due to copper oxides can reduce or eliminate this problem by changing to the Velan design. So how long does a Velan multi-segment bimetallic steam trap last? Answering that question requires concrete data, specifically comprehensive steam trap testing results. At Velan, we have compiled over 12 years of semi-annual survey data to provide the precise insights you need. At 150 psi service, Velan's multi-segment bimetallic design demonstrates a 10.5-year service life. In comparison, thermodynamic and inverted bucket traps on the same service average just over 4 years, meaning our design lasts more than twice as long as standard alternatives. Our data is backed by the 2011 white paper, Steam Traps and Mean Time to Failure, which analyzed a massive sample size of 4,656 life cycles to determine accurate long-term reliability. Velan steam traps are manufactured in compliance with all major international quality standards, using the most durable materials available today. A dedication to continuous product improvement and on-time delivery make Velan a worldwide leader in the design and manufacture of steam traps. For over 75 years, Velan has been the steam trap of choice when durability, rugged construction, energy efficiency, and critical drainage requirements are needed.